series-rated system is an electrical system where all components, including conduits, cables, and switches, are designed to work together as a unit to provide a specific level of protection against short circuits and ground faults. Several requirements must be met when designing and installing a series-rated system. Firstly, the type of equipment is important. All equipment in the system must be series-rated, meaning it has been tested and approved to withstand the specific level of fault currents expected in the system. Secondly, the component ratings are important. The components used in the system must be matched to the fault currents and voltage levels of the system. For example, conduits must be capable of handling the short circuit current without melting. Thirdly, consider installation methods. The equipment must be installed according to the manufacturer's instructions and in accordance with the National Electrical Code to ensure proper operation and protection. Fourthly, documentation is important. A fault current analysis or short circuit study must be performed to verify that the system meets the series rating requirements. This analysis should be documented and included in the project documentation. To learn more about series-rated systems, resources include National Electrical Code Article 408, IEEE Standard 1584, and articles on series-rated systems by Electrical Engineering Portal. Mike Holt has a booklet titled Series-Rated Wiring Systems that may be helpful. It is not a requirement that all equipment in a series-rated system be from the same manufacturer. However, it is recommended to use equipment from a single manufacturer as it simplifies the system design and ensures compatibility. National Electrical Code Article 408 covers switchboards and panel boards, which are often components within series-rated systems. This article provides requirements for the construction, installation, and protection of these components. It addresses issues such as overcurrent protection, conductor sizing, and working clearances. IEEE Standard 1584 provides guidance on performing arc flash hazard calculations. While not specifically focused on series-rated systems, understanding arc flash hazards is crucial in designing safe electrical systems, including those with series ratings. The Electrical Engineering Portal offers various articles and resources related to electrical systems, including detailed explanations of series-rated systems. These resources can provide additional insights into the design, application, and coordination of series-rated systems. Fault current analysis is a critical aspect of designing series-rated systems. This analysis involves calculating the magnitude of fault currents that could occur at various points in the system. These calculations are used to ensure that the components selected have adequate interrupting ratings and withstand capabilities. The short circuit study involves a comprehensive analysis of the electrical system to determine the potential short circuit currents at various locations. This study is essential for selecting appropriate protective devices and ensuring that the system can withstand fault conditions without causing damage or posing a safety hazard. A series-rated system relies on the coordination of multiple overcurrent protective devices, such as circuit breakers and fuses, to provide protection against short circuits and ground faults. The upstream device with a higher interrupting rating protects the downstream device with a lower interrupting rating, creating a series arrangement that enhances the overall system protection. When selecting components for a series-rated system, it is important to consider their interrupting ratings. The interrupting rating is the maximum fault current that a device can safely interrupt without being damaged. All components in the system must have interrupting ratings that are equal to or greater than the available fault current at their location. In addition to interrupting ratings, components must also have adequate withstand ratings. The withstand rating is the maximum fault current that a component can withstand for a specified duration without being damaged. The withstand ratings of components must be coordinated to ensure that they can withstand the fault currents until the protective devices operate to clear the fault. When installing equipment in a series-rated system, it is essential to follow the manufacturer's instructions and the requirements of the National Electrical Code. Proper installation practices ensure that the equipment functions as intended and provides the necessary protection against electrical hazards. The National Electrical Code provides comprehensive requirements for the installation of electrical equipment, including series-rated systems. These requirements cover topics such as conductor sizing, overcurrent protection, grounding, and bonding. Adhering to the National Electrical Code is essential for ensuring the safety and reliability of electrical installations. Single manufacturer equipment can simplify the design and coordination of series-rated systems. When using components from a single manufacturer, it is easier to ensure that they are compatible and that their ratings are properly coordinated. This can reduce the risk of misapplication and improve the overall performance of the system. Series-rated systems offer several advantages over fully rated systems. They can reduce the cost of electrical equipment by allowing the use of components with lower interrupting ratings. They can also improve system performance by providing better coordination of protective devices. However, series-rated systems also have some limitations. They require careful coordination of components and thorough fault current analysis. They may also be more complex to design and install than fully rated systems. When designing a series-rated system, it is important to consider the available fault current at each point in the system. The available fault current is the maximum current that could flow during a short-circuit condition. This current depends on the source impedance, the transformer impedance, and the conductor impedance. Calculating the available fault current is essential for selecting appropriate protective devices and ensuring that the system can withstand fault conditions. The impedance of electrical conductors plays a significant role in determining the available fault current. Conductors with higher impedance will limit the fault current, while conductors with lower impedance will allow a higher fault current to flow. The length, size, and material of the conductors all affect their impedance. Transformers also contribute to the impedance of the electrical system. The impedance of a transformer is typically expressed as a percentage of its kilovolt-ampere rating. Transformers with higher impedance will limit the fault current more than transformers with lower impedance. The source impedance represents the impedance of the utility power source. This impedance is typically very low, but it can still affect the available fault current, especially in large electrical systems. The National Electrical Code requires that electrical systems be protected against overcurrent, including short circuits and ground faults. Overcurrent protection devices, such as circuit breakers and fuses, are used to interrupt the flow of current when an overcurrent condition occurs. These devices must be selected and coordinated to provide adequate protection for the electrical system. Circuit breakers are automatic devices that interrupt the flow of current when an overcurrent condition occurs. They can be reset and reused after the fault has been cleared. Circuit breakers are available in a variety of sizes and interrupting ratings to meet the needs of different electrical systems. Fuses are one-time devices that interrupt the flow of current when an overcurrent condition occurs. They must be replaced after they have blown. Fuses are available in a variety of sizes and interrupting ratings to meet the needs of different electrical systems. Ground fault protection is designed to protect against ground faults, which occur when current flows from a live conductor to ground. Ground fault protection devices, such as ground fault circuit interrupters, are used to detect and interrupt the flow of current when a ground fault occurs. These devices are required in certain locations, such as bathrooms and kitchens, to protect against electrical shock hazards. Electrical grounding is an essential safety measure that provides a low impedance path for fault current to flow back to the source. This helps to prevent electrical shock hazards and ensures that overcurrent protection devices operate properly. Electrical bonding is the process of connecting all metal parts of an electrical system together to create a common ground. This helps to reduce the risk of electrical shock hazards and ensures that overcurrent protection devices operate properly. Arc flash is a dangerous phenomenon that can occur during a short-circuit condition. An arc flash is a release of energy in the form of heat, light, and pressure. It can cause serious burns, injuries, and even death. Arc flash hazard analysis is a process of evaluating the potential arc flash hazards in an electrical system. This analysis involves calculating the arc flash incident energy and determining the appropriate personal protective equipment needed to protect workers from arc flash hazards. Personal protective equipment, or PPE, is used to protect workers from electrical hazards, including arc flash. PPE includes items such as upgraded clothing, gloves, and face shields. The selection of appropriate PPE is based on the arc flash incident energy level. Electrical safety is paramount when working with electrical systems. It is essential to follow safe work practices and use appropriate personal protective equipment to protect against electrical hazards. Only qualified personnel should perform electrical work. Regular inspections and maintenance of electrical systems are essential for ensuring their safety and reliability. This includes checking for loose connections, damaged insulation, and other potential problems. Any problems should be corrected promptly to prevent electrical hazards. Understanding the principles of electrical safety is crucial for protecting yourself and others from electrical hazards. By following safe work practices and using appropriate personal protective equipment, you can significantly reduce the risk of electrical injuries. Always de-energize electrical equipment before working on it. Use lockout/tagout procedures to ensure that the equipment remains de-energized while you are working on it. Wear appropriate personal protective equipment, including arc-rated clothing, gloves, and face shields. Maintain a safe working distance from energized electrical equipment. Use insulated tools and equipment. Never work alone when working on electrical equipment. Be aware of your surroundings and potential hazards. Report any electrical hazards to your supervisor. Participate in electrical safety training. Stay up to date on the latest electrical safety standards and regulations. Electrical systems can be complex and dangerous. If you are not qualified to perform electrical work, do not attempt to do so. Hire a qualified electrician to perform any electrical work that you are not comfortable with. By following these safety precautions, you can help to prevent electrical accidents and injuries. Remember, electrical safety is everyone's responsibility. The available fault current is a critical parameter in the design and analysis of electrical systems. It is the maximum current that could flow during a short-circuit condition and is used to determine the interrupting and withstand ratings of electrical equipment. Calculating the available fault current involves considering the source impedance, transformer impedance, and conductor impedance. The source impedance is the impedance of the utility power source. This impedance is typically very low, but it can still affect the available fault current, especially in large electrical systems. Transformer impedance is the impedance of the transformer that supplies power to the electrical system. This impedance is typically expressed as a percentage of the transformer's kilovolt-ampere rating. Conductor impedance is the impedance of the electrical conductors in the system. This impedance depends on the length, size, and material of the conductors. The available fault current can be calculated using various methods, including hand calculations and computer software. Hand calculations are suitable for simple electrical systems, while computer software is typically used for more complex systems. It is important to accurately calculate the available fault current to ensure that electrical equipment is properly protected. The interrupting rating of an overcurrent protective device is the maximum fault current that the device can safely interrupt without being damaged. The interrupting rating must be equal to or greater than the available fault current at the device's location. Overcurrent protective devices with insufficient interrupting ratings can fail during a short-circuit condition, leading to equipment damage and potential safety hazards. The withstand rating of electrical equipment is the maximum fault current that the equipment can withstand for a specified duration without being damaged. The withstand rating must be coordinated with the interrupting ratings of the overcurrent protective devices to ensure that the equipment can withstand the fault current until the protective devices operate. Electrical equipment with insufficient withstand ratings can be damaged during a short-circuit condition, leading to equipment failure and potential safety hazards. Coordination studies are performed to ensure that the overcurrent protective devices in an electrical system are properly coordinated. Coordination means that the overcurrent protective devices operate in a sequence that minimizes the extent of the outage during a fault condition. For example, the overcurrent protective device closest to the fault should operate first, while the upstream devices should only operate if the downstream device fails to clear the fault. Coordination studies involve analyzing the time current characteristics of the overcurrent protective devices and adjusting their settings to achieve proper coordination. Time current characteristic curves show the time it takes for an overcurrent protective device to operate at different current levels. These curves are used to coordinate the operation of multiple overcurrent protective devices in an electrical system. The goals of coordination are to minimize the extent of the outage, protect equipment from damage, and ensure safety. By properly coordinating the overcurrent protective devices, you can improve the reliability and safety of the electrical system. Series ratings are a way to increase the interrupting rating of an overcurrent protective device by using it in combination with another overcurrent protective device with a higher interrupting rating. The upstream device with the higher interrupting rating is called the series connected device, and the downstream device with the lower interrupting rating is called the protected device. The series rating is the interrupting rating of the series connected device. Series ratings are permitted by the National Electrical Code under certain conditions. Firstly, the series connected devices must be tested and listed together as a series combination. Secondly, the protected device must have an interrupting rating that is equal to or greater than the available fault current at its location. Thirdly, the series connected devices must be properly coordinated to ensure that they operate in the correct sequence. Series ratings can be a cost-effective way to increase the interrupting rating of an overcurrent protective device. However, it is important to carefully consider the requirements of the National Electrical Code and to ensure that the devices are properly coordinated. Fully rated systems are electrical systems where all of the overcurrent protective devices have interrupting ratings that are equal to or greater than the available fault current at their locations. Fully rated systems are more expensive than series rated systems, but they offer a higher level of protection. In a fully rated system, any overcurrent protective device can interrupt a fault current without being damaged. This provides a greater margin of safety and reduces the risk of equipment failure. The choice between a series rated system and a fully rated system depends on several factors, including the available fault current, the cost of the equipment, and the desired level of protection. In general, fully rated systems are preferred for critical applications where a high level of reliability is required. Series rated systems can be a cost-effective option for less critical applications. Electrical codes and standards provide the rules and guidelines for the safe design, installation, and operation of electrical systems. These codes and standards are developed by organizations such as the National Fire Protection Association and the Institute of Electrical and Electronics Engineers. The National Electrical Code is the most widely adopted electrical code in the United States. It provides comprehensive requirements for the installation of electrical equipment and systems. The Institute of Electrical and Electronics Engineers develops standards for electrical equipment and systems. These standards cover a wide range of topics, including power systems, electrical safety, and electromagnetic compatibility. Adhering to electrical codes and standards is essential for ensuring the safety and reliability of electrical systems. Failure to comply with these codes and standards can result in electrical hazards, equipment damage, and legal liability. Electrical inspections are performed to verify that electrical installations comply with electrical codes and standards. Electrical inspectors are typically employed by local governments or insurance companies. They inspect electrical installations to identify any potential hazards and to ensure that the work is performed correctly. Electrical inspections are an important part of ensuring the safety and reliability of electrical systems. Regular inspections can help to identify and correct potential problems before they lead to electrical hazards or equipment damage. Electrical maintenance is the process of keeping electrical equipment and systems in good working condition. This includes tasks such as cleaning, lubricating, and testing. Regular maintenance can help to prevent electrical hazards, extend the life of electrical equipment, and improve system performance. Electrical troubleshooting is the process of identifying and correcting problems in electrical systems. This requires a thorough understanding of electrical principles and the ability to use testing equipment. Only qualified personnel should perform electrical troubleshooting. Incorrect troubleshooting can lead to electrical hazards and equipment damage. Electrical safety training is essential for anyone who works with electrical equipment or systems. This training should cover topics such as electrical hazards, safe work practices, and the use of personal protective equipment. Electrical safety training can help to prevent electrical accidents and injuries. Arc flash training is a specialized type of electrical safety training that focuses on the hazards of arc flash. This training should cover topics such as arc flash hazard analysis, personal protective equipment, and safe work practices. Arc flash training can help to protect workers from the serious injuries that can result from an arc flash. Grounding and bonding are essential safety measures that help to prevent electrical shock hazards. Grounding provides a low impedance path for fault current to flow back to the source, which helps to trip over current protective devices. Bonding connects all metal parts of an electrical system together to create a common ground, which helps to reduce the voltage between different metal parts. Together, grounding and bonding help to create a safer electrical environment. Surge protection is used to protect electrical equipment from voltage surges, which can damage sensitive electronic components. Voltage surges can be caused by lightning strikes, power outages, and other events. Surge protection devices, such as surge suppressors, are used to divert surge current away from electrical equipment. Surge protection can help to extend the life of electrical equipment and prevent costly repairs. Power quality refers to the characteristics of the electrical power that is delivered to a load. Poor power quality can cause equipment malfunction, data loss, and other problems. Power quality problems can be caused by factors such as voltage sags, voltage swells, harmonics, and transients. Power quality monitoring equipment is used to measure and analyze power quality parameters. This information can be used to identify and correct power quality problems. Power factor correction is used to improve the power factor of an electrical system. Power factor is a measure of how efficiently electrical power is being used. A low power factor can result in increased energy costs and reduced system capacity. Power factor correction equipment, such as capacitors, is used to improve the power factor. Harmonics are distortion in the voltage or current waveform. Harmonics can be caused by nonlinear loads, such as electronic devices and adjustable speed drives. Harmonics can cause equipment overheating, capacitor failure, and other problems. Harmonic filters are used to reduce harmonic distortion in electrical systems. Electrical efficiency is the measure of how efficiently electrical energy is being used. Improving electrical efficiency can reduce energy costs and conserve natural resources. There are many ways to improve electrical efficiency, such as using energy-efficient equipment, reducing standby power consumption, and optimizing lighting systems. Energy audits are used to identify opportunities to improve electrical efficiency. An energy audit involves a thorough assessment of an electrical system to identify areas where energy is being wasted. The results of an energy audit can be used to develop an energy management plan. An energy management plan is a roadmap for improving electrical efficiency. The plan should include specific goals, strategies, and timelines. An energy management plan should be reviewed and updated regularly to ensure that it remains effective.